Okay, so I will start from the point I stopped yesterday, and I will just very briefly recap what I was discussing. Okay, so we stopped with entanglement entropy, which is a very important quantity. I mean, I don't need to motivate here. So let me stress that differently from what I told you yesterday, knowing the entropy of a block is also important to get information about our ability to or our capabilities to simulate a quantum system, quantum many-body system by means of classical algorithms. So again, so I consider for simplicity a one-dimensional chain. I could take two parts, A and B, and the question is how the entropy of the block, since the ground state, in this case I'm talking about the ground state, the pure state, the entropy of the block tells me information about how much entangled region A and has with respect with B, and where this very important result by Calabrese and Cardi in one-dimensional system. So if you have a finite correlation length, the entropy obeys an area law. So essentially, the entropy scales like the boundary, which in one dimension is essentially a number, while if the system becomes critical, so the gap scales to 0, there are divergence, log-like divergence of the entropy with the system sides. This is reminiscent of the fact that you have power law decaying functions. Another thing, very important thing to be stressed is that I just mentioned yesterday, but let me say it again. It's the prefactor, which is a characteristic of the underlying conformal field theory. This is C is the central charge. Now, just to show you, I mean, this is just a plot I took from this recent review by La Florenzi in Physics Reports, which extensively describe all the progress that has been made on the study of essentially entanglement entropy in condensed matter system. So I think it took just a model in which there was some kind of spin model with a staggered magnetization, and by changing the degrees of staggering, we could look at states which went from gapped to gapless, and then you see that in the gap phase, the entropy rapidly saturates to a value which is fixed by correlation length, while the critical region you have log correction. I stopped here yesterday. That is, this behavior of the ground state makes it a special state in the Hilbert space. And this is something I would like to emphasize. We are not talking about, so if I take ground state, if we ground state of local Hamiltonians, the amount of the entropy quantified by the entanglement, the block entanglement entropy is not typical of a generic situation, but it's just a very special case. So far, I just described you the case of bipartite entanglement, where bipartite means that you just look entanglement between two regions. The two regions can be two sites or two regions, and various property tells you various things. But as I tried to explain at the beginning of yesterday's talk, in a multipartite situation, then essentially entanglement is not the only one which is contained in a bipartition. So one can ask different type of, so what is the entanglement contained in a much more complex situations. And now the question of multipartite entanglement or content of entanglement in a more complex partition is very difficult. And so I would say that just starting to consider various partitions is simply hopeless. So let's say in the literature, there's been several attempts to try to quantify, say, what is left behind, left out, from bipartition, just trying to give computable measure of entanglement, which capture not only bipartitions, but in general other sources of entanglement. Well, so let me start with metric, what has been called geometric entanglement, which was defined, which was introduced, I think, in the many body concepts by Way and Goldberg, in I guess 2005. That is a very simple idea behind it. It's just measure the distance of the state you want to consider from its closed product state. So it's essentially, you just look for the overlap of your states, the psi, for instance, the ground state, with a generic product states, and then you just find the maximum overlap. Okay, this is kind of a measure of how much do you have a question? No. How much entanglement is contained in your many body states. So weak point of this is that essentially it does not tell you what is the kind of origin of the entanglement, does not give you much information, but it just gives you a little bit of everything. And it's something not completely crazy to compute, especially when you have symmetries or you have an idea of the structure of the ground state. There are nice features here. So let me stress a few things. So by some reasons which are completely unclear as far as I know, so I mean this this geometric entanglement resembles the kind of area versus log L corrections that we saw for the entanglement entropy. This could be simply related to the fact that part of the entanglement which is encoded in these measures come from the entanglement entropy. This is possible. However, as far as I know, there is no real theory that shows why this is the case. Even, say, for instance, in one-dimensional spin system, the only thing, so as far as I know, the only kind of more solid result is this one by Roman Horus, who could just prove that the geometric entanglement is just bound by, so if you take a critical system, it could prove that the geometric entanglement defined in this way with this overlap. So the density, I mean, it scales like with n, but if you take per particle, then it's bounded by the entanglement entropy. So L, sorry. L is the dimension of the system. It should be n, because this is geometric. Sorry, this is this is a mistake. Sorry, I did not change this. I took a figure. So L is the dimension of the system. This is just the full system. Okay. A more interesting measure of multipartite entanglement, which comes originally from works done in metrology, is quantum Fisher information. So quantum Fisher information in metrology essentially tells you about, is related to estimation, and essentially tells you it's just quantify the distance, so how the state rho changes if you just do kind of, you apply this unitary operator. So essentially it tells you how sensitive is the state because of this unitary transformation. So I mean, essentially it's related to the fact that if you want to measure something, your thermometer or whatever should change substantially in order to appreciate temperature difference. I mean, this is the quantum version of that. And actually, again, in this context, it was shown that if you do m measurements of this variable theta, then the standard deviation of the estimate is bound by this quantity, which is the Fisher information. So what is the definition starting from the state rho? If you have a mixed state, so far I did not tell you anything about the connection to entanglement. This is just the definition of quantum Fisher information. If I start with a mixed state, expressed in its diagonal form, then Fisher depends in this way from the from these probabilities here and the various matrix elements of the operator O here computed between the various states alpha and alpha prime. Now, if the state is pure, then it becomes much simpler. It's just the variance of O computed on the state alpha. This is when this is the Fisher when the system is pure. Okay, I will not remind you because I will come back in a few seconds. Now, why Fisher information is related to entanglement? So a pure state said to be kappa k, sorry, not kappa k producible if it can be expressed as a product of at most k states. Okay, so if you know that the state is k producible but is not k plus 1, sorry, if it's not k producible, then you know that there is some k plus 1 multipartite entanglement. So essentially there are clusters of states, or sorry, clusters of qubits which are which cannot further decompose in smaller clusters. So in the example of 3 qubits I gave you yesterday, if you take GHZ states, these are tripartite, genuinely tripartite entangled state. Now, what these people essentially showed in this very nice work is that a very nice connection between this definition of multipartite entanglement and the Fisher information comes from considering the operator O I defined in the previous slide for the phase estimation in terms of sum of single site spin operator. So I will consider just spin 1/2. N is a generic unit vector that can be arbitrary. Now, the idea is that you just compute the Fisher information over all possible operate observables defined this way, meaning you change all possible direction n. If a state is separable, then Fisher information is bound to be smaller than n. In general, these people proved that if the Fisher information, the quantum Fisher information on the state rho is m times the number of, should be extended, okay? So it's larger than m, then you have m-partite entangled. So here, this expression is valid when m is the divisor of n, but I mean, essentially it does not really matter. So one can give a more complicated definition. So by using single site observables, it is possible to quantify how much entangled and what type of entanglement is present in the system. So this will, so for instance, if m is, so if the state is separable, this is essentially 1, m is 1. If this coefficient is larger than 1, then there is an amount of entanglements of m-partite. So you will find vectors, yeah, sure. But the idea is that you want to find, so in order to know if there is a kind of multipartite entanglement, you want to find the possible combination of directions that maximize this quantity. This is a witness, yes. No, it's not a measure, it's a witness. So you can say that it is large. So if it's larger, then there is tripartite or whatever. Yes. Yes. These are unit vectors. Yes. I'll give you examples. So in principle, you have to optimize over this capital N vectors. Yeah. But in some cases, you can use luck or intuition just to know. So for example, if you have a spin system close to a phase transitions, with some ordering along z direction, then you know that you expect that the variance along z direction would eventually diverge. So you expect that this optimization will work when these n are pointing all in the z direction. So in this case, you have a simple situation where this is, or you just try to use the fact that you have translational invariance, that this will help, so you simplify it. But in principle, I mean, complex. Okay, so let me give one specific example, which comes from a recent paper by Philip Hauke, Heil, Tagliacozzo, and Soller, that, I mean, they did the following. So they showed that, I will tell you, easy to see this. They show that this quantum Fisher information is related to just the retarded Green's function associated with the operator O that we are interested in. So the main point of, so one of the main points of their work was to say, oh, good, look, this is very nice because this G retarded is just linear response. So by doing some linear response, so we just couple our system to some operator which is coupled to O. We do linear response, and by just determine the response function, we are able to compute the Fisher information, and therefore we are done in trying to get information about the entanglement. So it is, I think, I mean, it's blah, blah way, but I think it's easy to understand this result, because as I mentioned yesterday, I think it was mentioned many, many times. So when you are in equilibrium and this expression holds in equilibrium, because of fluctuation dissipation theorem, essentially you can express all possible correlators in terms of a spectral function. And this is a way to say that the variance, let's say, consider that it's a pure state for simplicity, but essentially the variance is related to the retarded correlator. Now, so this is okay. Still, there is a big problem. That is, since the Fisher information is related to equal time, essentially it requires the whole frequency dependence of the retarded Green's function, which means that not only the low frequency, but also the higher frequency are important, actually, and I would like to stress for this for the next slide. Then you will see that actually at the given, so essentially the low frequency part is somewhat suppressed below so at finite temperature, okay? This is important for something which was mentioned, showed in the paper. That is, they saw that they consider an Ising model in a transverse field, and they consider both they consider both case in which they had quantum phase transition, low temperature, but also higher temperature. So essentially they find nice scaling. So this is in the at the value of the critical field as a function of temperature. They see that have kind of power law behavior. Now, one point which they made is that if you have a thermal transition, there is no trace of criticality in the Fisher information at at the thermal points. But I would say that kind of hand waving argument you can see from expression before is that from the expression before you can see that actually at finite temperature the low frequency part does not play a big role, and actually the singularity should appear in the long relaxation or time, and therefore there is no way in which one can observe this. Something different that you can do at finite temperature, and this is actually a work of where also Silvia participates. So any question I will on this slide I will not answer. Is that you can say, okay, instead of computing Fisher information on the canonical ensemble, an equivalent or possibly equivalent way, if the states thermalize, just to consider the Fisher information at the level of single eigenstates, okay, but just using ETH, as it was discussed also this morning by Laura. So differently from what happened with observables, actually, wherever even average values may coincide at the level of Fisher information, computing Fisher on a given eigenstate and using ETH will be different from its canonical expression. Just to remind you that here you should compute the mixed state expression, while here it's just a pure eigenstate where you are computing the Fisher. So you see, Fisher is in a sense is not an observable. So if you compute Fisher on an average state, this does not correspond to the average value you would get by computing on this on a pure state. I'll just mention this in this form because on Friday I will give you another example of a phase transition in which if the transition is signaled by quantities which are not observables, like entanglement, they are completely invisible to the average state, but can be detected at the level of a single realization. No, I did not say FD, but then I for the diagonal ensemble. This is the ETH and this is the Gibbs. So at the point that yes. Computed, yeah, with the top, yes. So in the case of FETH, you use just the variance of O. In the case of F Gibbs, you have to use the purity, the mixed state expression, in which you have to include also the probabilities, right? So they are computed on two different expressions. They do not. Okay, and since it's a nonlinear quantity, so the average of the quantity does not correspond to the quantity computed on the average state. The nice thing about, however, is this witness computed at the level of single eigenstate is that it just captures criticality. And therefore, it may become quite substantial if you are close to a phase transition. I think with this, I will, so I just conclude the discussion on the ground state, or in this last part of finite temperature, and I move to the next step of my discussion, that is what happens to the dynamics of so what happens to entanglement under non-equilibrium condition. So overall framework that I'm going to consider is just very simple yet very rich scenario, which is offered by what people call quantum quench. So I just prepare a state, psi 0, typically separable or with some entanglement localized somewhere, which on some Hamiltonian, I mostly will talk about Hamiltonians. And then after a while, I would like to know what is the entanglement content in the state psi of t. Now, as I'm going to show you here, it's not that I'm looking only at low energy states, but depending on the initial, I'm exploring the full spectrum. Okay, and indeed we will see that this makes a difference. If you wish, at the level of ground state properties, more or less what it counted was, what was important is just knowing if the correlation length was finite. Let's take the block entropy as an example. What was really important was that if the correlation length was finite or diverging. Okay, but many details of the Hamiltonian itself, of course, there are special cases, but many details were not really that important. They were just already included in the way correlation length was diverging in the critical exponent, but for the rest, no additional details were important. Now here, because we are looking also at the excited state, you will see that many properties of the Hamiltonian, being integrable, non-integrable, disordered, or just translation invariant, will play a very important role. And again, I'll follow this structure. I will start with a simple case, then I will add interaction, then I just correct the X view. I hope you appreciate this. I just noticed this morning because I'd forgotten. And then I will move to disorder. Okay, and you will see that while in the previous case, not much difference it was making, here you will see that the picture is way more rich. I will start with a very simple, and if you let me say it, pretty dull case, that is, so a very simple case. I mean, I just localize a bell pair on a one-dimensional side and and see what happens. Then very fast move to the much more exciting part in which the Hamiltonian itself will create entanglements. So the reason why I just start with this dull case is because, I mean, there are many, I mean, there are cases in which, so suppose that you have a spin chain, you just put a bell pair here. What happens is that because of the interaction of the spin, the entanglement, which is initially localized here, will spread. Okay. So from this picture, nothing special happens. So you would say, okay, so entanglement spreads like any other kind of observable. No, it may happen in special case, but actually the situation is much richer. And I will start with, again, with Calabrese and Cardi, who also studied the way the block entropy spreads as a function of time, starting from an initial separable state. Now, S of L is now the block entropy of for a block of dimension L. So what do we notice here? So starting from a zero entropy, state is separable. So first, the entanglement entropy grows linearly with time. First important thing related to the fact that somehow this information spreads. Yes. Yeah, I'm going to say yes. I don't, you spoiled the whole presentation. So, okay, I have to create some pathos, right? So otherwise, I'm joking. I'll be in 5 minutes. Okay, so this is just the ice model in a transfer system. So it's free fermions. So a couple of things to notice. So first, there is a linear increase related to some velocity of quasi-particle. Other thing which is very important now, the entropy in the saturates volume law. Okay, so excited state are involved. So in the steady, so in the long time regime, the entropy is proportional to L. Okay, and the saturation, sorry, the saturation time, so the time at which it crossover to scales with L. This is again spin the Ising model. Okay, now if I slightly complicate my life and consider an xxz, so still integrable but interacting, nothing really special happens. Still, I mean, this is pretty standard. I mean, these are not exceptional simulations, so, but I just took them for the presentation. So again, it's starts linear and then saturate to a volume law. And depending on, for instance, in this case, by the ZZ anisotropy, then since the velocity of this quasi-particle change, and so the growth of entanglement changes. In this example, Calabrese and Cardi gave very nice argument that explains essentially the whole behavior. So let me stress one thing: the fact that at a long time, there is a volume law is related also to the fact that it's very difficult to do numerical simulation as the time goes by. So by using classical algorithms. So let me stress, let me just spend some minutes on this argument, which I think is very nice, and it's worth looking at this. So the idea is the following. I'm starting with a separable state, but if I compare to the evolution Hamiltonian, it's just and kind of, it's a state at some finite energy density. So I can imagine that each point in space pairs of particles are emitted in a kind of entangled situation. In each point, the various pairs are incoherent, but they propagate. And so starting from a given point here, essentially the entanglement between region A and region B is related to the number of pairs in some units, the number of pairs that reached one of them region A and the other of them region B. Okay, so you just count. So just imagine you have one pair. If you have a single pair at the given time which remains in B, it means it did not coupled and therefore entangled A and B. But if there is a single pair which went one here, one component here, and the other in B, then this gives a unit of entanglement. So in this picture, the idea is that you have to, in order to compute the entropy of the region A, you have to compute the particle that started from a point, generic point X, and then flew, let's say in a symbol geometrical terms, after a given time. You can take velocity constant. It does not really matter for this argument. And they just move in such a way that X prime, so after a time t, X prime is in region A and X second is in region B. Forget about all these details. Essentially, it's very simple geometric idea. If you do this this integral, then you find exactly what to expect. You find that there is a first increase which is linear, saturation which is capital L. Sorry, now I call this is wrong. This is small l, and saturation occurs at the time of the order of L over B. Okay. Now I go to your question. So far, this is just integrable. Now, what happens if I move away from this? So let me start with there are a lot of papers, so I just select 2 or 3 just to give you what I think it's an interesting picture. So I start with this paper by Kim and Hughes, who did a simulation of the dynamics in Ising with the longitudinal fields. Now, I think it's they start with random initial states. So say in a good sense, the the numerical experiment was fine-tuned. So they chose parameters and other little things which were important to make their point clear, including, for instance, adding small boundary terms. But what they want to do is just to take a system in which, given the parameters, the energy would diffuse instead of spreading ballistically. So what they did was just to start with the state, which is the energy, which was localized in the middle of the chain. And they just wanted to study how it spread. So they quantified the spreading through the length R. So if you just essentially, they compute, sorry, I think this is wrong. So the square parenthesis should be inside, okay? So they compute this I minus n plus 1 over 2 times the energy. So if you, for instance, if you assume that the average Hamiltonian, the average energy spreads like an exponential, then you see that this R is just this length, okay? And they did some plots of the R of t as a function of time, and they saw that the energy spreads with the length, which is like square root of t. That's, yes. So, there are two mistakes, which that's okay. You should promise that on Friday you will not find the third mistake. So there are two mistakes. So first, the square bracket should be here, and this should be the average age. Okay, the average local age, which is time dependent. Okay, and this is yes, J, yeah, in units of J. Do you mean here, white saturate? I think yes, but I think they concentrate more on this region here. Okay, their interest was to show that there was the square root of t. No, this is a measure of how the energy spreads. Okay, sorry, I just write here the right formula. So this is R of t is 1 over the average energy times sum over I of I minus n plus 1 over 2 average local Hamiltonian. Okay. So yeah, so actually I should measure, let's say, on the bonds, okay? But let's ignore this. Okay, so if you assume that the H, so essentially at the beginning, the energy is localized in the center, okay? So n over 2. This is the initial state. There is some energy which is only in the central bond, and it's 0 everywhere. So if I plot the average energy, it's a function of I, and this is I. Then the energy starts spreading like this. And you measure this length. This length is R. Sorry? Yeah. I think it's yeah. So no, I think it's square. Yeah. But yeah. So let me say, how did they, I mean, this is what they describe in the paper. So there is not that they had to, they chose couplings in such a way that they could get for the system sides some region which was square root of t. And the reason why they wanted to emphasize this is that if you compute the entanglement, the block entropy is surprisingly identical to the integrable case. That is, I think it's shown here. So this is the square root increase. The entanglement grows linear. Okay. So this tells you that entanglement does not necessarily spread. So it's a spreading of information, so does not necessarily coincide with other observables. Okay. Yeah. So now I did not want to enter in this in the author. So I will concentrate. So there are some connections. So let me say at this level, the question is the linear. So obviously I cannot use the Calabrese-Cardi picture of ballistic particles flying because it does not apply here. Okay. So if it would apply, then there is no reason why the energy would grow like square root of t. So the question, but still entanglement grows linearly and then saturates as a volume law. So the question is, so why entanglement grows linearly? Okay, that's all. And okay. There are a few nice this paper, which came just after by Ho and Abanin, that they construct a symbol picture of this dynamics. So they had a look at the Rényi entropy S2. Okay, it does not really matter, but the nice thing is that if you just look at the entropy of rho A squared, then something easily that you can verify is that this trace is just trace of rho A squared if you take a basis, okay, of operators in the region A. So start with so you can express the rho A as just the average over this on OA on the state side. All right, this is very simple to, I mean, this is simple. So the idea was essentially, and this connects to what you said, on increasing time, then the original operator OA spreads out. Okay, so if you take just start with a single spin, then as a function of time, then you will get strings of Pauli operators. Okay, with coefficients that, however, should obey kind of sum rules, right? So the way the overall weight should be 1, and so by spreading out of the region, the weight of this, the contribution in the region A is decreased. And it is just this uniform spreading which of the information, which is essentially, which leads to this linear increase of entanglement, which is also something related to what you mentioned in terms of author. So let me just stress that I think I don't have time, but 2 minutes. 2. So I decided to stay with the Hamiltonian dynamics, but I really would like to stress that very nice progress has been done considering circuits. Okay, this is different types of dynamics. So you start with local bits of local dimension Q, and then what you start is just to create entanglement by just by applying different types of 2-qubit gates on even and odd sites. And so this is not a local Hamiltonian evolution, but as it was shown, I mean, the papers have different flavors, slightly different models. But the idea is that by considering these dynamics, consider random unitaries, one can make very nice progress, in particular when the local dimension of the Hilbert space increase, then it is possible to derive some analytical results. And actually, they show that the speed at which entanglement moves is not, so it's generically smaller than the speeds which governs operator growth. Okay, I think they coincide in the limit of Q to infinity. Actually, there are further results in this, in all the papers, but for instance, in this paper by Nahum, they show that while average entanglement grows linear in time, then the fluctuations of the entanglement in the block have a non-trivial power law dependence. But as I said, I mean, I think one should really do a set of lectures on this, and I'm sure you will hear a lot in the next week. So, and with this, I think I will stop and I will continue on Friday. Thank you. Okay. Thanks. Posso andare?